Well, hey folks, here we are, section 3.2. We're going to look at derivatives of products and quotients. And the first thing I'd like to go over will be the section objectives, so you can follow along in your book. In this video, I'm going to look at objective. The first objective is going to be differentiate products using the product rule. So that's going to be a new derivative rule for us. Then the second objective is we're going to apply the product rule to business functions. And third objective is going to be a brand new rule. It's going to be differentiating quotients using the quotient rule. So you can see right now this section, we're going to have two new rules, product rule and quotient rule. And then in objective 4, we are going to apply the quotient rule to a medication concentration. So here we go, folks. The product rule. Product rule says if your function h of x is equal to f of x times g of x, so a product of two functions, and f of and g are differentiable functions. That's just a fancy way of saying, hey, you can get derivatives for those functions. So look, if you have a product of two functions, then the derivative h prime of x is equal to f prime of x times g of x plus f of x times g prime of x. Okay, I kind of know this in the English, in an English form. Here's the English that matches up with the product rule. The thing about making it work is you have to notice that f of x is the first function, g of x is the second function. So when you have a product, the derivative, so h prime of x, the derivative is the derivative of the first function, that's f prime of x, times the second function, plus the first function times the derivative of the second function. And you're going to hear me say that quite a bit. You're going to hear me say derivative of the first function times the second function, plus the first function times the derivative of the second function, because I kind of remember the product rule in that English form. So let's see, first example here, differentiate the following functions. In part A, we're going to differentiate h of x equals 7x cubed times the quantity 2x squared plus 6x. Then in part B, we're going to differentiate the function f of x equals the quantity 7x squared plus x to the 4/3 times the quantity 5x to the 1/2 minus 9. So at this time, if you need to write these down, write them down, because I'm going to head off to the chalkboard and work out this example, worked out solution. So here we go, heading off to the chalkboard. All right, hey folks, we just looked at a brand new rule called the product rule. I thought I'd write it down up here in the upper right-hand corner of the board. So real quickly, the product rule says that if your function is a product of two functions, two differentiable functions of x, then the derivative is f prime of x times g of x plus f of x times g prime of x. Or in English, I like to think of it as the derivative of a product. The derivative is the derivative of the first function times the second function plus the first function times the derivative of the second function. And then here's where we left off, was the example, differentiate the following functions. And it's just I just want to practice using the product rule. So when I get the derivative here, I guess what I need to identify is 7x cubed. That's my first function. And the 2x squared plus 6x is the second function. See, I have a function times a function, and I'm going to call that one the first function. So according to the product rule, when we differentiate a product of two functions, derivative of the first function, so that's a 21x squared, times the second function. So derivative of the first function times the second function, plus the first function, 7x cubed, times the derivative of the second function. Oh, it looks like I'm going to go into this box here, so let me just kind of get rid of that. And
So now I need to do the derivative of the second function. Well, the derivative of 2x squared plus 6x is 4x plus 6. That's all there is to doing the derivative using the product rule. So that's it for part A. Now, yes, I could go ahead and distribute the 21x squared here and distribute the 7x cubed there, combine like terms, and that's what you'd be expected to do in the homework. But for right now, I just want to practice the product rule, not that algebra, just the calculus. So let's look at the second one here, part B. Get the derivative of f of x equals the quantity 7x squared plus x to the 4/3 times the quantity 5x to the 1/2 minus 9. So again, using the product rule, I have a function times a function. So function times a function. To get the derivative, I'm going to use the product rule. So one more time, product rule. The derivative of the first function. So that's the derivative of 7x squared plus x to the 4/3. The derivative of the first function is a 14x plus a 4/3 x to the 1/3 times the second function plus the first function times, now I have to do the derivative of the second function. So the derivative of 5x to the 1/2 minus 9, looks like that would be 5 times 1/2, that's 5 halves, x to the negative 1/2, and then the derivative of the constant is 0. So, whoa, look at that. That is the derivative of that function. And again, I'm not doing any algebra right now to simplify this down. I just wanted to practice using the product rule. So here's what I'd like you to do right now. Just practice using the product rule. I'd like you to pause the video, and in section 3.2, I'd like you to do number 15 and number 21. So go ahead, pause the video, and in section 3.2, do numbers 15 and 21. And after you've done them, restart the video, and I'll have a worked out solution for them. All right, hey, let's see if you were able to do number 15 and number 21 correctly. I have confidence that you were. So 15, you were asked to get the derivative of the function quantity 5x plus 3 times the quantity 3x cubed plus 2x squared plus 1. Product rule. See, you have a function times a function. So the derivative is the derivative of the first function. Well, the derivative of 5x plus 3 is 5 times the second function plus the first function. The first function is 5x plus 3 times the derivative of the second function. So the derivative of 3x cubed plus 2x squared plus 1 is 9x squared plus a 4x. And that's what I have for the derivative in number 15. Now again, I could distribute the 5, and I could FOIL this out and then combine all the like terms, and that's probably what you'll see in the back of the book, the answer in the back of the book. But I'm stopping right here. I just wanted to make sure that you got the calculus correct. Okay, number 21, the function was the quantity 3x to the 6/5 minus 5x times the quantity 4x to the 5/3 plus 2x minus 5. Again, product rule, you have a function times another function. So we crank this through the product rule. Product rule says derivative of the first function. Well, the derivative of 3x to the 6/5 minus 5x, oh boy, that's 18/5 x to the 1/5, then minus 5. So that's the derivative of the first function. Now times our second function, so we just bring the second function on down, plus the first function, 3x to the 6/5 minus 5x times, now we have to do the derivative of the second function, the derivative of 4x to the 5/3 plus 2x minus 5. And the derivative of this second function is, let's see, 4 times 5/3, that's 20/3 x to the 2/3 plus 2. Derivative of the constant 0. So here's the derivative for the function in number 21. Yeah, look at it. That's a big long mess. All right, hopefully you got 15 and 21. And now it's time to go back and we're going to look at an application of the product rule.
All right, now that we've looked at that example and did a couple of homework problems, numbers 15 and 21, it's time for us to look at an example of an application of the product rule. So let's look at this. Say it was determined that the price for a particular fall-themed house decoration is predicted to vary according to the function P of t equals 3.1 t squared minus 8t plus 45. And in that function, t is the number of weeks since August 1st, and P of t is in dollars. So that's kind of like our price function. The quantity of this item sold is expected to follow Q of t equals negative 4t squared plus 15t plus 120. And Q of t is the number sold, and again, t is the number of weeks since August 1st. So that's like our quantity function. So it looks like we have a price function and a quantity function. And what are we going to do here? Well, part A, we're going to find R of t and R prime of t. R of t, remember that's the revenue function. Kind of seeing what we're going to have to do to get the revenue function. Remember, revenue is price times quantity. Part B, we're going to evaluate R prime of 4 and interpret. And then in part C, we'll evaluate R prime of 6 and interpret. So if you need to pause the video to write this down, I suggest you do it because I'm getting ready to head off to the chalkboard to work out parts A, B, and C.
All right, hey folks, didn't write all the words down to the application that we just saw, but you know I will babble the words again. It was determined that the price for a particular fall-themed house decoration is predicted to vary according to the function P of t equals 3.1 t squared minus 8t plus 45. Keep in mind this function, t is the number of weeks since August 1st, and P of t is in dollars. So P of t is in dollars. It's kind of like our price, if you will. The quantity of this item is expected to follow Q of t, which is equal to negative 4t squared plus 15t plus 120. And again, t is the number of weeks since August 1st. So this is kind of like the price function, and this is the quantity function. So in part A, you're asked to find R of t and R prime of t. You're asked to find revenue. Remember, revenue is price times quantity. Take the price, multiply it by the quantity, that gives you the revenue function. So quite simply, the revenue function here is the price times the quantity. So it's a 3.1 t squared minus 8t plus a 45 times a negative 4t squared plus a 15t plus 120. That's the revenue function. Now we're supposed to get R prime of t, the derivative of the revenue function. Well, R prime of t is just the derivative of this function, and yep, look at this. You have a product of two functions, so you get to use the product rule. So again, the product rule says the derivative of the first function. It's a 6.2t minus 8 times the second function. Plus the first function, 3.1 t squared minus 8t plus 45 times the derivative of the second function. And I've run out of room, so I'm going to put the derivative of the second function times, I'm just going to put it right down here. That's negative 8t plus a 15. So it's this times that. Wow, now look at that. No way am I thinking of simplifying this. No way. Because when I look at part B, now part B asks you to evaluate r prime of 4 and interpret. I don't need my derivative simplified down. All I have to do is toss 4 in for the t's and see what I get. If I did this correctly on my calculator, when I put 4 in here for the t's, I put 4 into the t's in my derivative, I get r prime of 4 is 884.6. So now what does that mean? Well, remember, t was the number of weeks since August 1st. So this 4 means 4 weeks since August 1st. Let me write that down. 4 weeks since August 1st. Revenue. We're talking about revenue. Revenue. It's a positive number, so that means the revenue is not derivative. Remember, derivative tells us an instantaneous rate of change. So since it's positive, it means the revenue is increasing at a rate. Okay, remember, derivative, rate, it's an instantaneous rate of change. We need to have units. So it's increasing at a rate of, okay, that tells me the dollars. So it's $884.6 per, so it's a rate, so we need per week, because t was number of weeks since August 1st. So again, r prime of 4 equals 884.6, means 4 weeks since August 1st, revenue is increasing at a rate of $884.60 per week. In part C, I think I can get part C right here, folks. Part C, you were asked to evaluate r prime of 6 and interpret. Well, just like in part B, I'm going to put 6 into my derivative. Here's my derivative, so I'm putting 6 in for all the t's. And when I do that and crank that through my calculator, I get r prime of 6 is negative 1656.6. So now what does that mean? Well, the interpretation is almost exactly the same as this. The only difference is 6 weeks since August 1st. So the interpretation here, and I'm not going to write it down, I'm just going to babble it. The interpretation is 6 weeks. 6 weeks since August 1st. Revenue is, since it's negative, we would say the revenue is decreasing at a rate of $1,656.60 per week. So notice how it's almost exactly the same as this, except you'd have the interpretation. You'd have a 6 here, you'd have decreasing here, and you'd have 1656.6 here. So that's it for that example. Hopefully it's making sense and you're saying, whew, boy, I like this product rule. All right, let's head on back now and look at a new rule, the next rule in computing derivatives, which is the quotient rule.
All right, now that we have the product rule under control, it's time to look at the quotient rule. So here's the deal with the quotient rule. Quotient rule says if h of x is equal to f of x over g of x, and f and g are differentiable functions, then the derivative h prime of x equals f prime of x times g of x minus f of x times g prime of x, and all that junk over g of x, that quantity squared. And keep in mind here, g of x cannot equal 0. Going to give you the English. Here's how I interpret this. Here's how I know the quotient rule. For the quotient rule, you have to just look at the structure of your function, f of x over g of x, and notice that f of x is in the numerator and g of x is in the denominator. So when I do the derivative using the quotient rule, I'm going to say it's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. And then all of that junk over the denominator squared. So that's the English version of the quotient rule, and you're going to hear me say that quite a bit. Derivative of the numerator times denominator minus numerator times derivative of the denominator. All of that junk over the denominator squared. Let's see, our first example here, we're going to do two parts, A and B. We're going to practice using the quotient rule to differentiate the function in A, which is h of x equals 4x minus 9 over 12x plus 7, and the function in B, which is y equals 8x cubed minus 10x squared plus 5, all of that over 8x minus 9. So if you need to take a minute to pause this to write down these two functions, because I'm going to be heading off to the chalkboard to do a worked out solution for these two functions. So if you have to, go ahead and pause, write them down, because I'm going to the chalkboard.
Hey folks, the next rule that we just looked at is the quotient rule, and I thought I'd just quickly write down a version of it up here in the right hand corner of the board. So the quotient rule says if your function is a function divided by another function, quotient, division. To get the derivative, h prime of x, the derivative is, I'm going to babble the English again, the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, and then all of that junk is over the denominator squared. All right, let's practice the quotient rule, and here's the example that we left off with. Differentiate in part A, h of x equals 4x minus 9 over 12x plus 7. So there we go, the derivative. According to the quotient rule, the derivative says, the quotient rule says the derivative is the derivative of the numerator, which is 4, times the denominator, minus the numerator, now times the derivative of the denominator, which is 12, and then all of that junk over the denominator squared. That's it. And hey, you know what? Let me erase part B here. We didn't do it with product rule ones, but yeah, I kind of feel like, what the heck, let's do it here with the quotient rule. Let's simplify this a little bit. It doesn't take too much to simplify this. If you distribute the 4 up here, let's see, that gives you a 48x plus a 28. You distribute this 12, you'd have a minus 48x plus 108. And then all of that's over the denominator squared. And then if you combine like terms, 48x minus 48x, that's 0. 28 plus 108 is a 136. And that's over the denominator squared. So this is the result of the calculus, and then everything after that is just algebra simplifying. What the heck, we go ahead and do a little simplifying. So again, that's using the quotient rule. Using the quotient rule. Now let's look at part B. See, part B, I got to erase this, folks, so if you need to write this down, pause the video and write it down. Part B, your function was y equals 8x cubed minus a 10x squared plus 5, all of that over 8x minus 9. All right, so here we go, getting the derivative. I'll call the derivative y prime. Derivative. We take the derivative of the numerator. So that's a 24x squared minus 20x times the denominator minus the numerator 8x cubed. Boy, let me write that numerator down. Times, now the derivative of the denominator. Wow, that's just 8. That's not too bad. All of that junk over the denominator squared. Oh, what a mess that is. I'm debating. Do we want to simplify that or not? Yeah, let's just leave it as it is. The only simplifying we could do is to FOIL these two terms out here, distribute this -8, combine like terms, but we simplified part A. I'm going to stop here in part B, and that's the derivative. So at this time, what I'd like you to do is I'd like you to pause the video, and here in section 3.2, I'd like you to go into the homework, and I'd like you to try number 29. So go ahead, pause the video, try number 29. After you do that, we'll go ahead and restart the video, and I'll have a worked out solution for number 29. All right, here in number 29, you're asked to compute the derivative of the function f of x equals 4x minus 3 all over 2x plus 1. Very friendly one. Crank this through the quotient rule. So your quotient rule says the derivative of the numerator, which is 4, times the denominator, minus the numerator times the derivative of the denominator, which is 2, and then all that junk over the denominator squared. And you know what, for this one, let's go ahead and simplify this down. I mean, it doesn't take too much to distribute a 4 up here to get 8x plus 4. And it doesn't take too much to distribute. See, I think of distributing a -2. So that's an 8x minus 8x plus 6. And then combine your like terms. And you see in the numerator 8x minus 8x, that's gone. 4 and 6 is 10. So we have the simplified derivative as 10 over 2x plus 1 quantity squared. So hopefully you got that for number 29. And you feel pretty good about the quotient rule. So the next thing we would do is, let's go back and let's look at a quick example of applying our quotient rule.
All right, after seeing how to do the example, part A and B, and also doing number 29 from the homework, I think it's time that we look at an application of the quotient rule. So let's check out this function. C of t is 6.84t over 0.02, that should be a t squared, plus 3.28. So make a note, that should be a t squared. That's a typo. And this function describes the concentration of a certain drug in the bloodstream over a period of time. Now here, C of t is measured in micrograms per milliliter, and t is measured in minutes after the drug was first administered. So what are we going to do here? Well, we're going to evaluate C prime of 10 and C prime of 60, and we're going to interpret each. So probably what you need to do, write this function down. I don't know if you want to write down any of the other words. It might be in your best interest to, because I'm getting ready to head off to the chalkboard to work out this example.
All right, here we are going to work out this example, and by now I don't write down all the words from the example, just the important parts and pieces. So this function, C of t equals 6.84t over 0.02t squared plus 3.28. This function models the concentration of a certain drug in the bloodstream over a given period of time. C of t is measured in micrograms per milliliter, and t is measured in minutes after the drug was administered. So t is minutes after the drug was administered. C of t gives us the concentration in micrograms per milliliter in the bloodstream. Here you were asked to evaluate C prime of 10 and C prime of 60 and interpret each. All right, in order to do C prime of 10 or C prime of 60, the first thing we have to do is get C prime, the derivative of that function. Friendly application of our quotient rule. So here we go, quotient rule. Quotient rule says it's the derivative of the numerator. So that's a 6.84 times the denominator minus the numerator times the derivative of the denominator, and the derivative of that mess is 0.04t, and then all of that junk over the denominator squared. Okay, so there's the derivative. Now I'm just going to use the derivative to evaluate c prime of 10 and c prime of 60. So when I evaluate c prime of 10, notice I'm not simplifying that down. I don't even care to simplify it down because I'm just taking 10 and tossing it into the derivative for the t's, and I'm seeing what number comes out. So when I put 10 in for the t's, I get 0.314. So what does this mean? Well, the 10, t is 10. That means 10 minutes after the drug was administered. So we write that down. 10 minutes after the drug was administered. Okay, C was the concentration. So the concentration, now it's a positive number, folks, positive number, so that means it was increasing. Excuse me. Let me use that little symbol for increasing at a rate of, okay, 0.314, 0.314, and now my units, okay, remember the units for C. The units for C were micrograms per milliliter. So it was increasing at the rate of 0.314 micrograms per milliliter. So let me get that right here. Micrograms per, I'll just abbreviate milliliter as ml, per minute, because T was measured in minutes. So C prime of 10 is 0.314. So that means 10 minutes after the drug was administered, the concentration was increasing, positive, was increasing at a rate of 0.314 micrograms per milliliter per minute. On the other hand, when we do C prime of 60, we just toss a 60 into the derivative for the t's. When we do that, we get negative 0.083. So what does that mean? Well, T is 60. So it means 60 minutes after the drug was administered, the concentration was decreasing at a rate of 0.083 micrograms per milliliter per minute. I mean, it's the same structure as this interpretation. It's just that changes to 60. The negative means it was decreasing, and then that number goes there. So that's the example. Hopefully that's making sense. And you know what I'd like you to do? I'd like you to pause the video. Let's do one more of these. I'd like you to pause the video, and I'd like you to try number 65 in the homework. So go ahead and pause the video and go to number 65 in the section 3.2 homework. Try it. See what you get. Once you've done number 65, restart the video and I'll have a worked out solution. So go ahead, pause the video and do number 65. All right, folks, here number 65. It says here, in planning its future operating budget, the City of Rockton hires a consulting firm to determine the cost of removing the pollutants discharged into Lake Watson. They find the cost can be projected by the model C of x equals 113x all over 100 minus x. And notice the restricted domain, 0 less than or equal to x less than 100. X represents the percentage of pollutants removed, and C of X is the cost in thousands of dollars. So Part A, you were asked to find, use the quotient rule to differentiate C of X. So use the quotient rule and get the derivative. Well, that's kind of nice. Quotient rule says derivative of the numerator. That's 113 times the denominator minus the numerator times the derivative of the denominator. The derivative of the denominator is negative 1. That's not too bad. All over the denominator squared. Debating on whether or not I want to simplify this. It looks like it'd be pretty friendly to simplify. Let's go ahead and simplify this derivative. I mean, look in the numerator. You're just going to distribute the 113. And that gives you 11,300 minus 113x. And then a negative 113x times negative 1, that's plus 113x, all over the denominator squared. So you can see the minus 113x plus 113x, they cancel out. So this is one of those times when I opted to simplify the denominator because it just was, well, to be honest, it was easy and quick to do. But notice how it's going to help me maybe on Part B. See, Part B, you're supposed to evaluate the C of 50 and the C prime of 50, and interpret each. So here we go. First off, evaluate the C of 50. So you have to take 50, put it into the original function for the x's, and you should get C of 50. See, if I put 50 in here and 50 in there, I crank it through my calculator, I get 113. Well, what does that mean? Remember, x represented the amount of pollution removed in percentage, and this is the cost in thousands of dollars. So I would just quickly say the cost to remove 50% of the pollutants is, now this is in thousands, so I have to make sure I know that's in thousands. So it's $113,000. So the cost to remove 50% of the pollution is $113,000. That's an old problem. Evaluating a function and interpreting. Evaluate the derivative at 50 and interpret that. All right, so we got to take 50 and toss it into the derivative wherever we see the x's. This is where maybe the simplified derivative makes it a little easier for me to use my calculator. In any event, when I put 50 in here for the x and, good grief, I evaluate that, I get C prime of 50 to be 4.52. So now what does that mean? Remember, 50 is a percentage. So when the city is removing 50% of the pollutants, so when 50%, let me just rewrite that, is when removing 50% of the pollutants, the cost is positive number, so it's increasing. The cost is increasing at a rate of, keep in mind that's in thousands, so it's $4,520 per percent. So it costs $113,000 to remove 50% of the pollutants, and that cost is increasing at a rate of $4,520 per percent when they're removing 50% of the pollutants. So hopefully you got that for number 65, and hopefully you feel pretty confident now about cranking through the homework in section 3.2. Practice using the product rule and the quotient rule. So that's it for section 3.2. Thanks for watching.
All right, hey, we did this example, and we also did number 65, which was another application. So at this point in time, that's it in section 3.2, the product rule and the quotient rule. We've done several examples. We've done some applications. We've done some of the homework problems. So go ahead and get started in the homework and work through the homework in section 3.2. Thanks for watching.